This is ELC 131, Circuit Analysis 1, and this presentation discusses capacitor circuits with DC and pulse sources. Now, the Greek letter tau is the symbol for a time constant. Tau is measured in seconds. One tau, one time constant, is the period through which the charge on a capacitor changes by 63%. Mathematically, for RC circuits, tau equals R times C. So, for the circuit of figure 1, the time constant is 1 kiloohm times 1,000 microfarads, which is 1 second. So for the circuit of figure 1, the charge will increase across the capacitor in 1 second when the switch is in position 1. So looking at the circuit of figure 1, again, when the switch is in position 1, current will flow to charge the capacitor. And as the capacitor charges, the capacitor voltage will increase, and the current that flows to charge the capacitor will decrease. At some point, if the switch is left in position 1, the capacitor will charge to its maximum, which is the value of the source voltage. For figure 1, this is 10 volts. Now in figure 2, we see a plot of the capacitor voltage as a function in time. And again, in one time constant, for the circuit of figure 1, this is 1 second, the capacitor voltage will increase by 63%. So referring to the circuit, or to the plot in figure 2, at time 0, we assume the capacitor is initially uncharged. The instant the switch is placed in position 1, the voltage across the capacitor is 0 volts. However, at 1 second, the capacitor voltage will have increased by 63% to 6.3 volts. Again, this is 63% of the maximum voltage, 10 volts. At 2 seconds, the capacitor voltage will have increased to 8.6 volts. And this is equal to 6.3 volts plus 63% of 3.7 volts. 3.7 volts is the difference between the maximum voltage and the 6.3 volts that the capacitor starts charging from at 1 second. At 3 seconds, the capacitor will have charged to 9.5 volts, at 4 seconds, 9.8 volts, and at 5 seconds, 5 time constants, the capacitor will have charged to 9.93 volts. Now, the capacitor will never charge to 10 volts because this is an exponential growth or an exponential rate of increase, since during each time constant the capacitor voltage increases by 63%, it can never fully reach 10 volts. However, at 5 time constants, we assume that the capacitor is fully charged and the capacitor voltage is 10 volts. Now, in the circuit of figure 1, VR1 equals V source minus VC1. This is just Kirchhoff's voltage law at work. So figure 3 shows us a plot of the resistor voltage as a function of time. And again, at time 0, the instant the switch is placed in position 1, the capacitor voltage is 0, so the resistor voltage is 10 volts. At 1 second, The capacitor voltage is increased to 6.3 volts, so the resistor voltage is 3.7. And at 2 seconds, the resistor voltage is 1.4 volts. At 3 seconds, the resistor voltage is 0.5 volts. 4 seconds, 0.2 volts. And we assume at 5 seconds, 5 time constants, the capacitor voltage has reduced to 0 volts. Now, in the circuit of figure 1, I can be calculated using Ohm's law, VR1 over R1. So referring to figure 4, where we see a plot of current as a function of time, at time 0, again, the instant the switch is placed in position 1, the current flow through the circuit will be 10 milliamps. There's 10 volts dropped across the resistor. The resistor has a value of 1 k ohm, so the current that flows to charge the capacitor is 10 milliamps. 1 second after the switch is placed in position 1, the current will have reduced to 3.7 milliamps. At 2 seconds, 1.4 milliamps. At 3 seconds, 0.5 milliamps. At 4 seconds, 0.2 milliamps. And we assume that after 5 time constants, 5 seconds, the current will have reduced to 0. That at 5 time constants, we assume the capacitor is fully charged and no current flows to charge the capacitor. Now, referring to the circuit of figure 5, we've changed the position of switch 1, the single pole double throw switch, to position 2. And note that no current is now supplied by the source, Vs. And now that the switch is in position 2, the capacitor will discharge. And when the capacitor discharges, the capacitor is the source of voltage for the circuit. So current is now going to flow this way through the circuit as the capacitor discharges. And again, think of the capacitor as being the source of voltage for the circuit. As time elapses, the capacitor voltage will decrease, and probably more importantly, referring to the circuit of figure 5, note that the direction of current through R1 has changed. When the switch was in position 1, current flowed towards ground through R1. Now current is flowing away from ground through R1. And of course, if the direction of current through R1 reverses, the polarity of VR1 will reverse also. So note in figure 5, the polarity of the voltage across R1 has changed to negative to positive with respect to ground. Now, figure 6 provides us with a plot of the capacitor voltage as a function of time. Again, the one time constant for the circuit of figure 5, the time constant is 1 second. The charge on the capacitor and the voltage across the capacitor will decrease by 63% in 1 second. So we look at the plot of figure 6 and note the instant the switch is placed in position 2, this is time 0, the voltage stored in the capacitor, or the voltage across the capacitor, is 10 volts. At 1 second, the capacitor voltage has decreased to 3.7 volts, and this of course is a 63% decrease from 1 amp. At 2 seconds, the capacitor voltage will have dropped to 1.4 volts. Again, this would be 3.7 volts minus 63% of 3.7. At 3 seconds, the capacitor voltage will have dropped to 0.5 volts. At 4 seconds, 0.2 volts. And at 5 seconds, 5 time constants, the capacitor voltage will have decreased to 70 millivolts. Now again, the capacitor will never reach zero, the capacitor voltage will never reach 0 volts, because this again is an exponential decay. In each time constant, the voltage reduces by 63%. It will never reach 0. However, we assume that at 5 time constants, the capacitor voltage has reduced to 0 volts. Now, in the circuit of figure 5, since the capacitor is the source for the circuit, the voltage drop across the resistor and the voltage drop across the capacitor are equal. Now, we do have to include a negative sign here because the polarity of VR1 changed when the capacitor discharged. So referring to figure 7, which shows us a plot of the resistor voltage as a function of time, the instant the switch is placed in position 2, the resistor voltage is negative 10 volts. 1 second after the switch is placed in position 2, the resistor voltage is negative 3.7. At 2 seconds, negative 1.4. At 3 seconds, negative 0.5. At 4 seconds, negative 0.2 volts. And we assume that at 5 seconds, 5 time constants, the resistor voltage is 0. Now, the current during the discharge period can be calculated using Ohm's law. I equals VR over R. So the plot of current would look just like the plot of the resistor voltage. Now, E, Euler's number, is just a number kind of like pi. E equals 2.7818281828. And E describes the rate at which things change in nature. So E describes the rate at which population increases, the rate of radioactive decay, how your savings account grows because of the magic of compound interest, and more phenomena in nature. However, for this presentation, we're concerned about the fact that E describes the rate that the charge increases and decreases in a capacitor. Now, don't confuse E with EE on your calculator. EE is how we multiply values times 10 raised to some power. E is, again, just a number that is raised to a power. So on your TI-30X Pro calculator, the EE key is represented with the button shown. Now, with some calculators, this might be shown as E raised to the X power. But again, this depends upon which calculator you have. Now, our previous examples looked at calculating the capacitor voltage, the resistor voltage, and current at integer time constant values. And of course, we're going to have situations where we need to calculate the capacitor voltage, the resistor voltage, and current at any time. So the equations shown below provide us with a means of calculating the capacitor voltage at any time. So looking at the first equation, VC equals V source times 1 minus e to the negative t over tau. Note first that the capacitor voltage is symbolized with a lowercase letter v, which stands for an instantaneous quantity. Little t, or lowercase t, is the time at which we want to calculate the capacitor voltage, and of course tau is the time constant for the circuit. Now, with this equation, we assume that the capacitor voltage is 0 at the start of the charging period. Now, Kirchhoff's voltage law tells us that in this circuit, the resistive voltage equals V source minus the voltage across the capacitor. And we can also calculate the voltage dropped across the resistor using the equation shown, V source times E to the negative t over tau. And again, we use Ohm's law to calculate the current that flows to charge the capacitor, I equals VR over R. Now, during the discharging period, we use this equation shown, VC equals V final times e to the negative t over tau power, where VF is the final voltage that the capacitor has charged to. And again, during the discharging period, VR equals negative VC. And we can also calculate this by taking negative VF times e to the negative t over tau. And the current flow of the discharging capacitor can be calculated using Ohm's law, VR over R. So when we have an RC circuit connected to a DC pulse source, the capacitor will charge and discharge. Now, looking at the circuit of figure 8, the pulse period is 5 seconds, which is 5 time constants for the circuit. Therefore, the capacitor will fully charge and discharge. So the waveforms that we would see for the source voltage, the capacitor voltage, and the resistor voltage are shown in figures 9, 10, and 11. So the pulse goes from 0 volts to 10 volts, stays at 10 volts for a period of 5 seconds, and then goes to 0 volts and stays at 0 volts for a period of 5 seconds. So the capacitor begins charging at 0. Again, we assume the capacitor is initially discharged, and the capacitor will charge up to 10 volts through the period of 5 time constants. Then when the pulse source goes to 0, the capacitor will discharge, and the capacitor voltage reduces to 0 volts through the period of 5 seconds or 5 time constants. And looking at figure 11, again, the instant the pulse goes from 0 to 10 volts, the resistor voltage is 10 volts. As the capacitor charges, the current decreases, the resistor voltage goes to 0. And the instant that the pulse goes from 10 volts to 0 volts, now the capacitor acts like, or is, the source of voltage for the circuit. Current will flow back in this direction as the capacitor discharges, and of course the polarity across the resistor will be positive to negative as shown. Through the period of 5 seconds, the capacitor discharges completely, and the voltage across the resistor will be 0 volts. Now, in figure 12, we look at an example of a circuit with, again, a DC pulse source. Yet note the frequency of the source voltage is now 1/10 of the time constant of the circuit. So the capacitor will not fully charge or fully discharge. Now we have to modify the equation shown when we looked at the charging and discharging of a capacitor, because we have to take into account the initial voltage across the capacitor. So for this circuit, we calculate the capacitor voltage by taking the applied voltage minus the initial voltage times 1 minus e to the negative t over tau, plus the initial voltage. And during the discharging period, the capacitor voltage equals V final times e to the negative t over tau. So note, because the positive pulse period is only 1/10 of the time constant, the capacitor does not fully charge to 10 volts. Now, the 0 volt period of the pulse waveform is not long enough for the capacitor to fully discharge, so the capacitor only discharges to about 2.4 volts. Then the capacitor charges to about 5.5 and discharges to about 3.3 volts, I think. And note, after 3 cycles of the pulse source, the capacitor then reaches more of what we think of as steady conditions here, where the capacitor charges to 6 volts and discharges to about 3.7 volts, charges to about 6.2 and discharges to about 3.85, and charges to about 6.2 and discharges to about 3.9. And the capacitor will continue. If this graph went on to the right, the capacitor would continually charge to about 6.1 volt and discharge down to about 3.9. And in electronics, we use this sort of circuit to perform the mathematical operation of integration. And if you've taken calculus, you remember that integration is finding the average of a function, with respect to time. Now, looking at this circuit of figure 12, notice the source voltage goes from 0 volts to 10 volts. It's assumed to have a 50% duty cycle, which means the positive period equals the 0 volt period. So the average of this voltage, the average of the source voltage is 5 volts. And notice that if we look at the waveform that we see across the capacitor, that this waveform goes above and below 5 volts. So this circuit would be used to obtain the average of a changing voltage, or what we call an integrator. And we'll look at this circuit as we progress in subsequent classes, in particular ELN 131 and ELN 132. Now, the last thing we'll look at is using a capacitor to smooth out or suppress voltage spikes and voltage drops, or voltage sags. So we see a circuit in figure 14 that has a 5 volt DC source, a source resistance of 100 ohms, and then a 1 microfarad capacitor in place in parallel with the 10k ohm load resistor. Now, it's not uncommon for our source voltage to have voltage spikes, and we see in figure 15 a 5 volt spike occurring on the supply line. And again, this voltage spike could be caused by lightning nearby. It could be caused by electrical equipment such as motors or welders or other sources of electromagnetic energy. So the source voltage goes from 5 volts to 10 volts very rapidly. However, what happens is when that source voltage increases so quickly, current flows this way to charge the capacitor. And since the capacitor voltage increases at this exponential rate, the capacitor voltage only increases a small amount, and again the capacitor voltage is equal to the load voltage. These components are in parallel. Now when the voltage spike drops from 10 volts back to 5 volts, of course the capacitor is going to discharge, and the discharge current actually flows back in the opposite direction. But let's just say that we remember that the capacitor discharges at an exponential rate. So when the voltage drops from 10 volts to 5 volts, the capacitor voltage decreases and the subsequent load resistance decreases. So even though we see a 5 volt spike on the source voltage, the load only sees an increase of about 0.5 volts. Now, likewise, we can see sags or dips in the supply voltage. This could be caused by the supply or the service into our home or business dropping down momentarily, or other electromagnetic sources of energy. So we see here that the source voltage goes from 5 volts down to 0 volts. And as this happens, of course, the capacitor has charged to 5 volts here. And when the source voltage drops, the capacitor is then going to supply current to the load resistor. And this keeps the load voltage somewhat constant. Even though we see a 5 volt drop in Vs, the load voltage only drops to about 4.5 volts. And again, as the source voltage goes from 0 back to 5 volts, the capacitor is going to charge and keep the voltage across the load resistor somewhat constant. So even though we have these spikes, have a spike of 5 volts, notice that the load voltage only goes up to about 5.5. Even though we have a dip of Vs to 0 volts, the load voltage only drops to about 4.5. And of course, if our load were some kind of digital system, an Arduino or other programmable system, we know that we can't have the voltage get too large to this load because it could damage or destroy the load. And also we can't let the voltage drop too far because this could erase, or it won't erase the program, but it could erase data, and it could or will cause the programmable system to reset. So in this presentation, we looked at the time constant for RC circuits, the charging and discharging of a capacitor in a circuit with a DC source, and we looked at the response of RC circuits with a pulse source. We looked at a similar circuit where the time constant of the RC circuit is 1/10, or excuse me, where the pulse period is 1/10 of the time constant of the circuit. And we use this circuit to perform the mathematical operation of integration. And we ended with looking at placing a capacitor in parallel with a load so that we can smooth out voltage spikes and voltage dips from the source voltage.